right, well, if you're just tuning in, hi. You guys can chat with me at any time. Just use the either remind or use the chat box on YouTube. You just need to be logged in your YouTube account. And we're going to get started. So what we're covering tonight are all the topics on your Unit 3 test: L'Hopital's, curve sketching, tangent line approximations, particle motion, and existence theorems. And we're going to kind of fly through these. If you have questions at any time, just send them. We will go over whatever you guys have questions about. And remember, if you're watching this later, you can always rewind, fast forward, whatever you need to do. So we're going to get started, just making sure that you guys are aware. These are your learning targets. They're on your review sheet. So go through and check them off as you go. Make sure you know what each of those are. If you can do each of those, you're going to be good to go. Also on your review sheet, you guys have or on your unit overview, you have this. So this is a summary of everything that is on this test. There's all your curve sketching. There's your particle motion. The only thing not on there is L'Hopital's rule. So we're going to start with that because it's sort of the most basic, and it's also the one where we've got to be very careful with our notation. So L'Hopital's rule is a method for finding limits when they're in an indeterminate form. And what we're going to do is we're going to say, okay, we're starting with some kind of a quotient or something that can be rewritten as a quotient. And the limit of the top and the limit of the bottom are both 0, or the limit of the top and the limit of the bottom are both infinity. So we're getting an indeterminate form, either 0 over 0 or infinity over infinity. Whoops. So if that happens, what L'Hopital's rule says is that it equals the limit of the derivative of the top over the derivative of the bottom for either scenario. Okay, so very quick AP note. You must show the limits separately. You need to show the limit of the top and the limit of the bottom separately. Make sure that you do that or you'll wind up losing points because 0 over 0 or infinity over infinity are not defined values. And because of that, we can't have that as, something that we're equal to. So make sure that you're showing each of those separately. Okay. Not to distract you, but the climbing is amazing. You're welcome. Santa's great. Okay, so let's look at these two limits. So if I plug into this, and I'm just going to do it in my head really quickly, I see that if I plug in, I get ln of 1. I know that's 0 over 0. So I know in my head that this is giving me 0 over 0, but I'm going to be very technical with what I write here. So I'm going to say, okay, the limit as x approaches 0 of my numerator equals 0. And the limit as x approaches 0 of my denominator equals 0. That is enough for me to say, therefore, L'Hopital's applies. It is okay if you write L'Hopital's applies. It's okay if you spell it wrong. What is not okay is for you to say LH applies, because LH is not a thing. You just made up that abbreviation. So make sure that you're saying L'Hopital's there, okay? Now, what does L'Hopital say? Well, it says that that derivative will be equivalent to the limit as x approaches 0 of derivative of the top over derivative of the bottom. And so what that gives me is 1 over 1 times 3 over 5. So that limit is just 3/5. All right, we're going to do one more that's a little bit varied, and then we'll go at this one. I'm going to tell you guys this is a graph of f of x, and we are going to try to find our limit. So first of all, if I take the limit as x approaches 3 of the numerator, I see that's 0. Limit as x approaches 3 of the denominator, I need to get from the graph. Still 0, right? So I'm going to take those limits separately. So limit as x approaches 3 of x minus 3 equals 0. Limit as x approaches 3 of f of x equals 0. Therefore, L'Hopital's applies, not LH, right? L'Hopital's applies. So what L'Hopital's tells me is that that will be the same as the limit as x approaches 3. Notice the value that you're approaching doesn't change, of 1 over f prime of x. So that would be 1 over f prime, which is the slope of this graph. So my slope at that point is -1. So that would just be -1. A lot of the times on the AP exam, you will see them in this form because there are other ways to figure out other limits, but there is no way you can do this one without L'Hopital's. So that's part of the reason why you'll see them with multiple representations a lot. Okay, send questions as you have them. Other than that, I'm going to keep moving on. So we're going to go back to curve sketching. Generally, guys, curve sketching has been something you've been really strong on. We are not going to do every question from this, but I'm going to at least hit high points and things that we tend to miss a lot. So justifications, again, very quick points to hit. Once you've made the statement that you want to make, stop writing. The more you explain, sometimes the more likely you're to get stuff wrong. Make sure that you know the difference between like increasing and saying the derivative is positive. Those both in a student's mind can mean the same thing. The problem is if you say f is increasing, you've done no calculus, right? So if you mean to say that f is increasing, say f prime is positive. Okay, make sure that you're using calculus. And avoid using pronouns. No it, no the velocity, technically that's like a replacement for saying v of t in justifying behavior, anything like that. No pronouns, name the function by its name. All right, so let's look at a couple of these. Again, a lot of these you know. F will be increasing when f prime is positive. F is decreasing when f prime is negative. Relative mins and maxes, so I'm going to have a relative min when f prime changes from negative to positive, a relative max when f prime changes from positive to negative, and a point of inflection when f double prime changes signs. A lot of people will think, oh, point of inflection, that's just where my second derivative equals 0. It's stronger than that. You actually need to have a sign change there. So make sure that you specify that. Concavity. This is something we're going to talk about a little bit further in depth. So f is concave up, and from f double prime, I know that's when f double prime is positive. It's concave down when f double prime is negative. Notice, nothing to do with maxes and mins, right? Concavity has to do with the second derivative. Now, the question I would ask myself is, okay, well, when is f double prime positive? And let's explain that from f prime. So for f double prime to be positive, which is the slope of f prime would need to be increasing because that would mean it has a positive slope, which would mean that its derivative would be positive. So same thing here when I'm talking about f double prime being negative, I need f prime to be decreasing there. So if you're looking at a graph, sometimes you might be like, I have a graph of f prime, how am I going to figure out concavity of f? Well, think about if f prime is increasing, then f double prime would be positive because f double prime is the derivative of f. And then we'll go from there. Again, not something that you guys were struggling with a ton on your quiz, but just clarification if we needed it. Common mistake, what's wrong with this sentence? So there's a max at x equals 3 because f double prime is negative, so f is concave down. What you need to know is that f can be concave down anywhere on this. So like on that, f is concave down on the entire domain, all real numbers. Just because f is concave down at a point does not mean that it's a maximum, right? So we need to go further with that. We're going to look at the second derivative test for that. So just hang on. If that's something that you've had questions about when we use concavity for max and mins, and when we just use it, like that's something we're going to get into further, okay? All right, so let's do a couple practice questions. We are not going to do all of these. I'm going to kind of pick and choose, but we will look at ones that I think we tend to have mistakes on. So the first thing is a question like this. So the equation of the tangent line of the curve at its point of inflection. So point of inflection, the biggest mistake I tend to see is people just thinking it's where the second derivative equals 0, but it is actually where the second derivative changes signs. So that's really what I'm looking for. Okay, so let's find that point of inflection, and then we can write the tangent line. So y prime would be 3x squared minus 6, or 12x. Y double prime would be 6x minus 12. So this has a 0 on the second derivative at x equals 2. And I need to confirm here that that's actually a critical value. It's actually a sign change. It is, luckily, but it will not always be. So here, there's a sign change to the right of 2, it would be positive. To the left, y double prime would be negative. So I know that my critical value is at x equals 2. I'm sorry, my point of inflection. Now let's find the y value there. So y would equal 2 cubed minus 6 times 2 squared. So 8 minus 24. So that would give me negative 16. And so my point that I'm dealing with here is 2, negative 16. Now it says find the equation of the tangent line to the curve. So I know that I'm going to be doing y plus 16 equals something times x minus 2, but let's think about that slope, right? Slope of the tangent line is the value of the derivative of your function at that point. So we're going to look at y prime at that point and see what we get. So this would be 3 times 4 minus 12 times 2. So that's 12 minus 24. So this is negative 12. So already I can eliminate anyone that has positive 12 as a slope. So I'm eliminating that one and that one. And then going from there, y plus 16 is negative 12x plus 24. So y equals negative 12x plus 8. And a lot of what it's looking at there is algebra mistakes. So make sure that you're actually being careful with your algebra. All right, continue to send questions as you have them. Let's look at another second derivative one. For what values of x will this be concave downward? Concave downward should make you think second derivative. Downward should make you think negative, right? So I'm going to find the second derivative of this, and I'm going to see where it's negative. So y prime is going to be, now I'm going to actually rewrite this as 2x minus 4 to the negative first. I think it's easier to do with power rule. You can do this with quotient rule if you'd like. But that's going to be negative 2x minus 4 to the negative second. And times 1, derivative of the inside is 1. So y double prime is going to be 4x minus 4 to the negative third. So this is 4 over x minus 4 to the third. And so looking at intervals where this would be concave downward. So fractions equal 0 when the numerator equals 0. The numerator of this will never equal 0, so don't worry about that. Denominator, that is going to equal 0 at 4. So I know that my only possible point of inflection here is at 4. So let's plug in some values. If we plug in a number lower than 4, we're going to have a negative cubed, which will be negative. If we plug in a number larger than 4, we're going to have a positive cubed, which would be positive. So I do see that this changes signs. Where is it concave down? Anywhere on the interval where my second derivative is negative. So that would be anywhere that x is less than 4. Now let's say those had both come out to be positive. It would be no values of x. Totally fine. All right. Let's look at... we're not going to do this one, but let's just talk about this really quickly. So how would you find where f has points of inflection? So this is f prime. So remember, for points of inflection, you're looking at change of signs in f double prime. Okay, that's what we're looking at there. So knowing that, I would need to find the derivative of this, which you could do using either product rule or multiplying that out, and then find where it actually changes signs. We're not going to do that. It's the same kind of thing we've been doing, but if you would like to, it's a good exercise. And I will put this whole document up on my teacher site. All right, let's look at this one. So f prime is this, where one of the terms we don't know, it's g of x, but we know g is continuous, and we know g is always negative. So where is f increasing? So first thing I'm going to ask myself is, okay, what does that mean? So to me, this means f prime is positive. So this is f prime, at least I'm given that. So let's try to figure out where this would be positive. So g of x is always negative. It doesn't have any zeros, so I don't need to worry about that. But there's a 0 here at negative 1, and there's a 0 here at positive 2. So those are my zeros. So now let's actually try plugging in some numbers. So let's say I plug in a number less than negative 1. So this would be negative. This would be positive because it's a negative in the parentheses, but it's squared. And this is always negative. So here I've got a negative times a positive times another negative. So that's going to come out to be positive. Now, looking at negative 1, if I plug in a number between negative 1 and 0, which would be like 0, this would be positive, this would be positive, this would be negative. So I know that's going to come out to be negative. And then if I plug in a number greater than 2, this is going to be positive, this is going to be positive, and that's going to be negative. And you could also figure that out by looking at the fact that at 2, this is tangent to the x-axis. It doesn't actually cross. So where would f be increasing? It is only increasing from negative infinity to negative 1. Make sure you actually check all the intervals. Okay, let's look at this one because now we're given a graph. And so this is one that can be tough for people. So you're given the derivative of f. So this is f prime. Always important to know what you're actually looking at, right? Which of the following could be the graph of f? So let's notice a couple things. Number one, f prime is always positive, right? Which means that f is always increasing. So it cannot be A, B, C, or D. I'm sorry, A, B, or C. Could be D. So f is always increasing. So now what I'm looking at here is, okay, well, what's it kind of doing? So here, my slope should be close to 1. And then as it goes out, my slope should approach 0. So let's look at which one of these does this. Here, maybe the slope's close to 1, sure. But as this goes out, the slope gets steeper. Versus this one, my slope is close to 1. But as this goes out more, the slope approaches 0. So this would be choice E. So make sure that you're looking at not only where are the zeros and is it positive or negative, but you can look at the patterns too of how it's growing. Okay, let's look at another one. So at which of the 3 points on the graph of f will f prime be greater than f double prime? All right, so critical analysis, and you couldn't even see me reading that. Okay. So where will f prime be greater than f double prime? Usually when they say that, they're thinking about one being negative and one being positive. So remember, f prime is going to tell you whether f is increasing or decreasing. And f double prime is going to tell you about concavity. So I'm going to go with the obvious here. Let's pretend that f prime is positive. So that would mean that this is increasing, right? And f double prime is negative. So that would mean this is concave down. So is there a time where it's increasing and concave down? And by it, I mean f. That is not how you spell down. Good spelling. Okay. So here, it's decreasing and concave up. So there, you would have f prime negative and f double prime positive. So it's not A. At B, you would have f prime positive because it's increasing, and f double prime negative because that's concave down. So that is a point where that occurs, right? At C, you would have f prime equal to 0, and you would have f double prime negative. So that is also a point where that happens. So there's actually 2 places here where your f prime is greater than your f double prime. And that is at C and B. So letter E would be your choice. All right, let's talk relative minimum because this is something that people can get tripped up on. Relative min versus relative max. And actually, before we do this, let's just talk about that. So relative versus absolute extrema. So a couple of reminders. Number one, relative extrema cannot occur at endpoints. They do not ever, right? Relative extrema means in the neighborhood. You have to look from both sides. Absolute extrema can occur at endpoints. So like if you look at this one, that is not a relative extrema because we don't know what's happening on the other side of it. It's not an absolute extrema either because it's not the lowest or highest overall. But this one, even though it's not a relative extrema, is the lowest on the whole domain. And so as a result, or really on the whole range, as a result, that would be your absolute extrema, right? So to find a relative extrema, that is where you are finding where the derivative equals 0, right? Finding the critical values, or where f prime does not exist. And then you are testing with a sign chart. And by sign chart, I mean like A and then like plus, minus, whatever. Okay? That's the way that we would find relative extrema because you're looking for that actual in your graph. Now, if I want to find absolute extrema, this is, first of all, it must be on a closed interval. If you don't have a closed interval, you are going to have to do a lot more arguing to tell me that something's absolute because you're going to have to tell me that it like never gets bigger than this or never gets bigger than that based on its behavior. So if it asks you about a closed interval, typically you're looking for absolute. Then you are going to find critical values, right? So find critical values, which again are where f prime equals 0 or where f prime is undefined, which, I mean, I'll label this is critical values, right? And then you are going to plug in critical values and endpoints to the original. So this is your Jeopardy game, right? This is watching Wolf Blitzer bomb at Jeopardy. So you are looking at your endpoints and looking at any other critical points in the interval. Now remember, if you are not in the interval, that's like me sitting on my couch at home yelling at the TV. I might know the answers. I'm not a candidate to win the game, right? So think about the candidate test for that. So if I'm doing relative extrema, let's do this one first and then we'll do an absolute. So for relative extrema, where does this have a relative minimum? First of all, it says x value, so I know I only need the x, not the y, but that can be important. So let's look at this. So this would be 24x to the 5th minus 24x squared. That would be my derivative. I'm going to set that equal to 0 because it's never undefined. So this would be 24x squared times x cubed minus 1. Now, that is a difference of cubes, and so you can factor that, or, I mean, we could probably guess here, the only real number value that's going to make that equal 0 would be x equals 1. So, and then this one would be at x equals 0. So you have two critical values. So I'm going to make my sign chart at 0 and at 1. And I am going to test these. So let's plug in, remember, to the derivative, to f prime or whatever your function is. We're going to plug into that. So at 0, I see that that's, what did I factor out? X squared? That's x squared. So it should be tangent there. So let's see what side it is and then go from there. So this should be negative, negative, because you are plugging in a value less than 0, so even though that's positive, that's going to be negative. And then if I know it changes signs there, so it switches. So where does this actually have a relative minimum? Anywhere it goes from negative to positive, because that would mean your slope goes from negative to positive, so x equals 1. Okay, let's do an absolute extrema, and then we'll do a graph, and then we'll move on. So absolute extrema, again, look, it gives me that closed interval, right? So I want the absolute extrema of this on the interval from negative 5 to 3. So first of all, the first thing I normally do on these is I make my chart. So I'm going to say let's plug in negative 5, and let's plug in 3. So if I plug in negative 5, it is 125 plus 60 plus 23. So that is 148 plus 60, so 208. And if I plug in 3, I've got 27 minus 36 plus 23. So that is 50 minus 36, which is 14. So I can already tell that 3 will not be my absolute max, and negative 5 will not be my absolute min. So now let's see if there's any other critical values on that interval. So f prime of x would be 3x squared minus 12, which is 3x squared minus 4. So this would have zeros at negative 2 and positive 2. Those both happen to be on that interval, so you do need to test both. So negative 2 and positive 2. And remember that I'm plugging back into f, because I want to know if it's the biggest or the smallest on f. So if I plug in negative 2, I've got negative 8 plus 24 plus 23. So that's 47 minus 8, which is 39. And if I plug in positive 2, I've got 8 minus 24 plus 23. And so that's going to be 7. So now find the absolute extrema. That means the y values, right? It doesn't say where they're located. So y values. So your absolute max is 208. Your absolute min is 7. So what I would say here is that there's an absolute max of 208, and you can say at x equals negative 5 because you're always going to be covered then. You've said where it is and you've said what it is, so you're covered in both directions. And there's an absolute min of 7 at x equals 2. And you're done. All right, let's do one of these from the graph, and then we will move on from curve sketching. So This is a graph of the derivative of f. The first thing you always want to identify is what you're actually looking at, right? So next thing, for what values is f increasing? So when I'm looking for f increasing, I think, okay, f needs a positive slope, which would mean f prime is greater than 0. So I'm going to, so anywhere f prime is positive. Now f prime is negative anywhere below the x-axis, positive anywhere above. So because my interval only goes to 4, this is happening from 1 to 4. And you'd say because f prime is greater than 0, right? Do not say because f is increasing. For what values of x does f have a relative minimum? So relative min means you're looking for a sign change. So I'm looking for f prime changes from negative to positive. Negative to positive. This is me writing notes to myself, by the way. You should not be writing negative to positive. Okay? So this would be at x equals 1. And that's it. And you'd say f prime changes signs from negative to positive. Do not write that sloppy stuff that I just write. That's just a quick note because we're booking through this stuff. All right, where does x have a relative maximum value? So there I'm looking for where f prime goes from positive to negative because I'm looking for a positive slope to a negative slope, right? Now, that never happens on this. So no values of x. There are none, right? So none. Now, where is f concave up? Here's where we got to put our thinking pants on. So, f is concave up when f double prime is positive. We know that, right? When does that happen? Well, that happens when f prime has a positive slope, so increases. So, I'm looking for anywhere on this graph that f prime is increasing. So, from negative 4 to negative 3, it's going up. From negative 1 to positive 3, it's going up. So this would be negative 4 to negative 3, union negative 1 to 3. And your answer would be because f prime is increasing. Okay. 9 we're not going to do, but just so we saw it, find the maximum value of the derivative. So you would find the derivative and then find the max. So find the second derivative and look for a sign change. Notice that's not on a closed interval. So what that tells me is I'm looking for the relative maximums because they didn't give me a closed interval. All right, second derivative test. Most of you guys are pretty good at this, but make sure you know the second derivative test is when we talk about concavity and extrema. So first of all, the first derivative has to equal 0 there because it has to be a flat point. And then we can look at the concavity. So if the first derivative is 0 and the second derivative is positive, meaning it's concave up, f is concave up, then this would be a min. If the first derivative is 0 and the second derivative is negative, that would be a max. So that's one way you can tell. So if I looked at one like this, where, okay, that's f of negative 7, sure, that's just the original. I know that the derivative of f is 0, so this means there is a horizontal tangent at x equals 7, right? And the second derivative is negative, so that means this is concave down. So what that tells me is there's a horizontal tangent, so it's flat, but it's concave down. That is how I know that there's actually a maximum. So I know that negative 7, 6 is a relative max on f. Now, if it actually said to use the second derivative test, here's what I would do. This is my first function, that's y. So y prime is cos of x, right? And we need to know where cos equals 0. So 0 equals cos x at, let's see, think about our unit circle. So cos is the x value, so at pi over 2 and at 3 pi over 2. And then I'm going to test those in the second derivative. So y double prime is negative sine x. So y double prime evaluated at x equals pi over 2 is negative sine pi over 2, right? Which is greater than 0 because, less than 0 because that negative up front. So that would tell me that y is concave down, which means there would be a maximum, which is not what they wanted me to prove, but that's okay. And y double prime evaluated at x equals 3 pi over 2 is negative sine of 3 pi over 2, which is positive. Now that tells me that y is concave up there, which means we have a minimum. So there is a relative min, and you would write this out, I'm abbreviating because we're going fast, at x equals 3 pi over 2, because y prime evaluated at x equals 3 pi over 2 equals 0, and y double prime evaluated at x equals 3 pi over 2 is positive. Now you could write that out in words also. All right, we're going to move on to linear approximation. If you have questions, send them. You guys are so quiet tonight. All right, so linear approximation, all this means is find the tangent line and plug in the value you have to get a good estimate. So I know that this is a point. I know that that's my derivative at that point. What is the tangent line approximation of negative 3.1? So first thing you see when you see that is write the tangent line. So I'm going to do y minus 4 equals x plus 3. That's my point. My slope is 2, so there's the tangent line. Whoops. To get the tangent line approximation, you're just going to plug in for x. So plugging in there, I would have y minus 4 equals 2 times negative 0.1. I almost think it's easier sometimes to think about these as fractions. Just make sure you can deal with them. So y equals negative 0.2 plus 4, and so that is 3.8. All right, let's look at the last one of these. Let f be a function set with f of 1 equal to 4, so there's a point where this is your slope. Okay, so that is like dy dx, or f prime. So find the slope of the graph at 1. So that's going to be 3 times 1 squared plus 1 over 2 times 4. So that is 4 over 8, which is 1/2. Now, there's my slope. I have my point. Write a tangent line and approximate that. So it'd be y minus 4 equals 1/2 x minus 1. Plug in 1.2, so y minus 4 equals 1/2 times 0.2. And so that's y equals 0.1 plus 4, which is 4.1. All right, moving on. Particle motion. I am not going to spend a lot of time on this because truthfully, you guys rock at this. If you need more help on something in particular, great, come see me or go see Miss Belden or email us. But I honestly think, based on your particle motion quizzes and just your knowledge of physics, you guys are great at this. 2 things that I want you guys to be careful with, and this is really it, and then we're going to move on, is first of all, be careful with speed, right? So speed, look at the sign of velocity, look at the sign of acceleration. If they match, it's speeding up. If they don't match, it's slowing down, okay? Now, for this one, and this is big, and I know in Miss Bowden's class you guys just talked about this. If you're given a function like s of t or x of t, and you are not given v of t or a of t, do not start writing v of t and a of t unless you've defined them. So, for instance, if I tell you s of t equals x squared plus x, you are not allowed to say v of t equals 2x plus 1 unless you've done this. You've said, okay, well, I'm going to define this as s prime of t. And now it's defined. Now here's the other thing. You've only defined it here as v of t. You have not defined that as velocity. Right now to us, v just means the letter v, right? It's a symbol. So do not say, well, velocity is positive. Well, I'm going to say, what's velocity? So unless you say v of t, which is the velocity of the particle at time t, just don't do it. So when you're talking about this, if you're talking about speeding up or slowing down or acceleration, I would talk about s of t, s prime of t, s double prime of t. So I would not define, unless you define them otherwise, be very careful with that. All right, we're going to skip those because I honestly think, well, let's do this speed one. So when is the particle speeding up if the graph below is v of t, the velocity of the particle? So notice here, it's defined v of t, and it's defined it as the velocity of the particle. So that's important. So speeding up, I am looking for v of t and v prime of t, notice I did not say a of t, to have the same sign. So one of the ways, there's a couple ways you can think about this. Some of us look at this and go, okay, if v of t is positive, v prime of t also needs to be positive. So that means v of t is positive and v of t is increasing. That's one way to think about it, right? Or v of t is negative and v of t is decreasing, because then v and v prime would have the same signs. That is one way to do it, and it totally works. So positive and increasing, negative and decreasing, those would be your two intervals. Now you could also make yourself a sign chart if you wanted to. You could do, okay, v of t, it only changes signs at 6, and v prime of t is going to change signs a little bit more often. So that changes at 2. And then it changes at 7, right? Those are your max and mins. So V is positive here and negative there. And then this is positive, negative, 0, negative. Really, I could have split that up more. And then positive. So what you're really looking for is overlap. So like these are both positive here. And these are both negative from 6 to 7. I should have drawn that better with 6 over here, if 7's right there. And so your intervals here would be 0 to 2 and 6 to 7. Okay. Last thing we're going to talk about is existence theorems. And this is something that people tend to just get confused on because you haven't studied the definitions enough. So, intermediate value theorem and mean value theorem, those are the big two on this test. So the intermediate value theorem states that if it's continuous on the closed, then f of x takes on every value between f of a and f of b. So, in other words, it says if I've got this function and I know it's continuous here, there's f of a, there's f of b, right? I have to hit every value between those. That's what that says. So if that's a and that's b, every value between f of a and f of b is covered. So here's what I would say. If you're given f and it's talking about actual f, so if you're given f and it talks about f, that is usually IVT. And I know that this is review from Unit 1, but that is an existence theorem, and it's something we're going to practice more on our review day tomorrow, is distinguishing between those. Somebody just asked, will there be review questions from past units? Only in, not specifically, only IVT, but we're going to practice with that more, because one of the things you really need is distinguishing between IVT and MVT. But really, you're going to have a limits question, and you're going to have derivatives. So this all kind of builds. There's always review. Okay, MVT is what we just did, and that says, mean, think average, that if we are continuous on the closed and differentiable on the open, then there is a number where f prime of c equals f of b minus f of a over b minus a. In other words, the slope of the secant line equals the slope of the tangent line, right? So the picture usually looks something like this. You've got this. Here is your secant line that connects those, and that's continuous and differentiable. And you're looking for parallel tangent lines, so maybe like there and there. And so like this would be a C value, and that would be a C value, where those are parallel. And you guys did great with this on Class Friday. So what you're looking for here is that you're given a function like f, and you're asked about f prime. Because notice with IVT, you're given f, and then they ask you about f. We did that before you ever knew what a derivative was. We did that back in our first unit. But on this one, you need to be able to find a derivative to calculate that. So typically you can distinguish between these because if you're given a function and you're asked about its derivative, that will usually be MVT. Versus if you're given a function and asked about the function, then that will be IVT. So let's do a couple of these. So if I look at this one, G is differentiable. Does G have a 0 on the interval from 4 to 7? Justify. So notice I'm given G and I'm asked about G. To me, that screams IVT. I mean, this saying IVT above it might also scream that, but that would be one thing I would look for. So does it have a 0? So I'm looking for a time when G equals 0. So let's look at our endpoints. At 4, G equals 9. At 7, G equals 2. That does not scream 0 to me, right? So sometimes we need to look a little closer. So I know at, 4.5, G equals 3. And at 6, G equals -4. So actually there we're guaranteed a 0. So here's what I would say. Since G is differentiable, it is continuous. So since they didn't tell me it was continuous in the question, I'm stating that. On the closed interval, so I would say the closed interval I'm using, 4.5 to 6. And we know that G of 6 is less than 0, which is less than G of 4.5. Right? We know that that's sandwiched in there. So since G is continuous and this is true, there exists a C on 4.5 to 6 such that G of C equals 0. Now, that didn't really answer my question because the question asked on 4 to 7. So you could say since 4.5 to 6 is a subset of or is contained within 4 to 7, there exists a 0 on 4, 7. And that's like the hardest IVT we'll really get, because on that one, you have to really think about what's going on there, right? Sorry. Could you simply say G, or would you have to say G of X? You can just say G. It's good. Now, same thing for this one. Would G equal 6.75 at least once? So find a place where it's above it and below it, so maybe there. And then make the same argument. Since G is continuous on the closed interval from 4 to 4.5, and 6.75 is greater than G of 4.5, but less than G of 4, then there would exist a C on that interval where it would equal 6.75. All right, and then the last thing is MVT. Let's do an MVT. So verify that f of x satisfies mean value theorem, or square root of x. Okay, cool. On the interval from 9 to 25, then find the numbers that are guaranteed by it. So I'm going to ask, is this continuous, and is it differentiable? Is it continuous? Well, it's a radical function over the interval from 9 to 25. It's never discontinuous, right? There's nowhere it's undefined. And is it differentiable? Radicals are smooth functions. They will be differentiable. So here's what I could say. Since, not in highlighter, since f is differentiable, and you are writing that out, not writing diff, on the open interval and continuous on the closed interval, and you can just write the interval, you don't need to write closed interval. If you just wrote the closed interval and didn't specify 9 to 25 there, you would lose a point, because I need to know what closed interval, right? So since this is true, by MVT, and here's what MVT says. There exists a value between 9 and 25 such that, and ST is an approved abbreviation, such that f prime at that value equals f of 25 minus f of 9 over 25 minus 9. Now, it asks you to actually find those C values. So, let's find them. So, f prime is 1 over 2 radical x. And f of 25 minus f of 9 over 25 minus 9 is 5 minus 4. Nope, 5 minus 3. So 1/8. And let's find where they're equal. So 1 over 2 radical x equals 1 over 8. Cross multiply or just set your denominators equal. Radical x equals 4. And so square both sides, x would equal 16. Now, is that on the interval? Yes, it is. Great. So this C value is 16. Okay, so my class, we're going to review more tomorrow, but please let me know if you have questions, concerns. I'm going to be here for about 5 more minutes, and then I'm rolling out. Me and Santa, we're making our moves, and you guys can send me other questions as you work. So I'm going to hang out for a couple minutes. Send me questions, Remind or YouTube. Either is good.